Well, welcome to another session of RDWorks Learning Lab. Today we're not going to touch anything to do with RDWorks because we're going to be using this session to look at mirrors. The mirrors don't rank very high in the list of important things that you should keep an eye on, but in fact they are probably one of the most important parts of your machine because they're the things that carry the light from the laser tube down to the cutting head. And if you've got dodgy mirrors, you're losing power along the way. Now, when I did my last test here, I thought I had something like about 8 watts of loss across 3 mirrors and a lens, which is a horrendous loss. So today what I'm going to do is to try and see if we can find out where that loss is occurring and why. And I'll also try and explain a little bit more about mirrors and reflectivity to you. So we're going to start off by doing a power test. And I've set my machine to 60% power, which I think will make it fire up at 20 milliamps. And that's the maximum that I should be running my tube at if it was a 50 watt tube. In fact, I think it's a 40 watt tube, so probably it should only be running at about 18 milliamps. But hey, what the hell? When it goes, and I shall replace it with a proper 50 watt tube. I've got the nozzle off. And we've just got an unfocused beam that sits on this surface here of my meter. And once we start the program off, you'll see that the head is moving around in a spiral pattern so that we don't have any possibility of etching off the anodize on this surface. So we've got our meter set to 0 and we will just run the test now. Now at the moment all it's doing is moving slowly out towards the edge. And once it gets towards the edge, it'll switch on the beam. And there we go, we're running at 19.5 milliamps. And it's running for 20.2 seconds, which is the recommended length of time for this particular meter. And we can now watch the meter climb gently. You can probably see that it's just about peaked there at 32. So we've got 32 watts of power down at the end here. So I'm just going to reset my meter again, and what I'm trying to do is to get it back to room temperature. Well, I've got a little container full of room temperature water that's been left in this workshop here, and so if I move it around in here, it should quickly get me back towards room temperature. And there we go. So we'll just dry it off nicely, and you'll see without me touching the 0, it's come back to room temperature. So what I now want to do is check the power into the mirror, which is effectively the power out of the second mirror. I would say we made to about 30.7. And this time we don't have so much of a fight because we've only got some backwards and forwards motion here. So I can sit here in the beam. I would say we just about made 37.8. And here we are coming straight out the tube. Yeah, I'd say 38.2. Right, now I've just been away to put these results down and sort of try and analyse exactly what they mean. And as you can see here, we've got 38.2 watts coming out of the laser itself, and the first mirror transmits 37.8 of those 38.2 watts, which is a transmission of 98.9%, which is not bad. I'll talk about expected percentages in a minute. Now when it comes to the second mirror, we've got 37.8 watts going in and 34.7 watts going out. Now that's an efficiency or a reflectance of about 92%, but it means that we're losing 8% of our power through that one mirror. The next mirror down, where we get 34.7 watts going in and only 32 watts coming out. Now that again is a transmission factor or reflectance of about 92%. Now 8% is an unacceptably high value. The sort of mirrors that we need for these machines, we can comfortably live with about 98 or 99%, and they're going to be fairly cheap mirrors. Now if you're using an industrial laser where possibly you might be firing 5 kilowatts at the first mirror, for example, 5,000 watts, if you lose 1%, you've lost 50 watts. If you lose 2%, you've lost 100 watts. Now the question is, where does that 100 watts go? And the answer is to heat up the mirror. Everything starts to get out of proportion then. You have to have mirrors which have got cooling built into them to absorb that heat. So with an industrial laser, you will probably be looking at paying a lot of money for a mirror that could be up as high as maybe 99.5, 6, 7 or even 8% reflectance. Very high, but a very high cost. Now we don't need to spend that sort of money on these machines because, you know, we're only losing 2% of whatever we're putting in. Even if it's 2% of a 100 watt laser, then you're only losing 2 watts, and 2 watts into the mirror will easily dissipate into the air. So we don't have a problem with needing to buy expensive mirrors, but what we do need to do is make sure that we do get the best out of the mirrors that we have got. They might be cheap, they might be cheerful, but they'll still be pretty good reflectors, as you can see here. Now I'm half suspecting, and I haven't checked yet, but I'm half suspecting that the mirrors on this machine are just probably gold plated glass. Something called K7 glass, which is gold plated, which means that as soon as we break through the gold plated surface, the glass underneath is in fact an absorber of infrared. That's not good news. So we're going to have to investigate what's going on with these last 2 mirrors here very shortly, because maybe I've been a bit aggressive with my cleaning and I may well have broken through the gold film. We shall have to see when we examine them closely. Okay, now my mirrors come out quite easily, well at least this one does, because it looks as though it's only a screw thread holding it in. So if I rotate this disc here, I shall have to make a special tool up for this, but please excuse me for me wanting to rush and see what sort of mirror I've got in there and what size it is. I shall just get a cotton wool bud so I don't do any damage, and hopefully I should be able to just lift that out of there. So first of all, let's clean the mirror with some isopropyl alcohol. I'll examine the mirror surface to see if there's any damage on it. It had a little bit of film on it, a little bit of black film. Quite a lot of marks on the surface there when I look at it with my eyeglass, and I'm being quite aggressive, as you can see, with my cleaning. But little by little, I have to say, I am removing most of the debris that seems to have been burnt onto that surface. This looked like quite a good mirror till I looked at it under 8 times magnification. I'm going to try something slightly more aggressive on here, which is acetone, which is still considered to be a reasonably good material for cleaning lenses and mirrors. Now this doesn't look like glass, could be stainless steel. It's not magnetic, which is good news. So I've now cleaned that mirror up with acetone and with alcohol. I've got the mirror back to quite a nice clean finish. There was obviously something burnt onto the surface of the mirror. Now on this mirror here, the mirror is obviously in this piece here. This is the fixed piece, and this is the piece that moves. And I'm going to have to take that piece off. Yeah, if I undo these screws, these are the spring screws, these are the setting screws, so when I put it back on it should be more or less in the right place. They've got posi drive screws or Phillips head screws on there, and there's just not enough space to get in there with a screwdriver. What we really need is a key. We need some cap edge screws on there, so when I take that off I shall have to replace them with little cap edge screws which I can use an Allen key on. Okay, well we've managed to get our mirror off now. We should be able to undo this again. Oh dear. Well, I don't think there's any doubt you can see what the problem is there. I haven't had my finger in there, but whatever it is, it's not a finger mark. So let's go at it quite aggressively with some acetone. You see, I'm actually being quite aggressive with this. I wouldn't normally do that, but I was prepared to throw the mirror away and start again and make my own copper mirrors even. And I might still make some copper mirrors, because if they perform better than these, whatever they are, it's nothing to do with the reflectivity of the surface, as I've shown you. You know, you can get extremely good reflectivity because it's crystallographic at a certain wavelength. So this is what you're seeing here is visible light reflection, not infrared light reflection. Well, let's give that a try with some isopropyl alcohol. There's still just a hint of a mark in the middle there, but to the naked eye it looks quite good now. It doesn't look half bad actually. I think that's going to be a substantial improvement. And there we go, that one's gone in without me touching it. And you'll see what I mean about these silly screws. Okay, this time we've got some cap head screws so that we can adjust these up with a key. We've probably got more to get hold of to put them in by hand as well. Okay, now that I've cleaned the mirrors, let's see what sort of results we get. Okay, let's jump straight to the results. Have I made an improvement? No, is the short answer. So what am I aiming for? Even the cheapest mirror should give me about 98%. And then I'm also led to believe that I wouldn't expect more than about a 1% loss across the lens. So that brings me down to a total of 35.4 watts that I'm expecting to see at the workface. It seems very strange that I've cleaned those mirrors and made the situation worse, but I've got to accept the fact. Now that probably means that I'm forced into a corner now where, as I need something fairly quickly to keep me running, I'm probably going to have a go at making my own copper mirrors. Now copper mirrors, 25mm diameter, about 3mm thick, would normally cost somewhere in the region of about £25 or £30 for this sort of machine, to probably a 99% transmission quality. If I was to go for industrial quality mirrors, then they would probably be up in the £200 to £300 region, which I'm certainly not prepared to spend. I could save myself a lot of money if this works. So the story doesn't end here, and I think making copper lenses and still trying to track this problem down is the subject of the next video.